Right now, there are objects moving through space that will outlive everything you know. They will outlive your children's children's children. They will outlive the pyramids. They will outlive the concept of nations. And the strangest part is that we built them in the 1970s with less computing power than the phone in your pocket, and then we sent them away forever. What they're doing out there, in the space between stars, is something we never fully planned for. Something that reveals a truth about the universe we're only beginning to understand. There are 5 spacecraft that have achieved escape velocity from our Sun, 5 machines that will never fall back. They are moving through a region of space that no human has ever studied directly, and what they're finding doesn't match what we expected. But to understand why that matters, you need to understand how we got them there in the first place. And that story begins with an accident of geometry that happens once every 175 years. In the mid-1960s, a physicist named Gary Flandreau was running trajectory calculations at the Jet Propulsion Laboratory when he noticed something unusual about the upcoming decade. The 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, were going to align in a way that happens only twice in the span of an average human civilization. If you launched a spacecraft at exactly the right moment, you could use each planet's gravity to slingshot toward the next one, visiting all 4 worlds in a single mission. Without this alignment, visiting all 4 would take separate missions, separate decades, separate generations of engineers. With it, you could do everything in 12 years. The plan that emerged was called the Planetary Grand Tour. 4 spacecraft, 3 planetary flybys each, a complete survey of the outer solar system before the alignment window closed. By 1969, NASA had assembled a working group to develop the mission. The projected cost came back at over $1 billion. Congress looked at that number, looked at the space shuttle program they were trying to fund, and killed the Grand Tour in 1971. What replaced it was something smaller, something that could be justified on paper. 2 spacecraft from the Mariner program, designated Mariner 11 and Mariner 12, would visit Jupiter and Saturn. That was the official mission. That was what Congress funded. But the trajectories were designed with a secret built in. If the probes worked, if they survived the radiation, if the cameras held up and the instruments stayed calibrated, then the path they were on would allow them to continue onward to Uranus, to Neptune. To fulfill most of the Grand Tour's original objectives without ever asking for permission, this is the part that matters. The entire mission was a gamble disguised as a modest proposal, and the engineers knew it. They built machines that could theoretically last decades for a mission that was only funded for a few years. They installed instruments they might never get to use. And they launched them into the dark with the understanding that the real mission wouldn't begin until the official one was over. Mariner 11 and Mariner 12 were renamed just months before launch. The new name was Voyager, Voyager 1 and Voyager 2. The names matter because they became synonymous with the farthest reach of human ambition, but the numbers are backward. Voyager 2 launched first, on August 20th, 1977. It was placed on the longer, slower route, stopping at all 4 giant planets in sequence. Voyager 1 launched 16 days later, on September 5th, and almost didn't make it to space at all. The launch was turbulent, nearly catastrophic, but it recovered. Once in flight, it followed the faster express route, visiting only Jupiter and Saturn before heading out of the solar system entirely. It overtook Voyager 2 in mid-December, somewhere inside the asteroid belt. Both spacecraft carried 11 primary instruments, cameras that could see invisible light and radio wavelengths, spectrometers for infrared and ultraviolet analysis, plasma detectors, particle counters, magnetometers, everything needed to sample environments that had never been sampled before. But there was something else on board. Something that wasn't an instrument at all. A golden record. 12 inches in diameter, gold-plated copper containing sounds and images selected to represent Earth. Music, greetings in 55 languages, the sound of a human heartbeat. Instructions for playback were etched onto the cover, along with a pulsar map showing Earth's position relative to 14 neutron stars. The record was coated in uranium-238, an isotope whose decay rate could theoretically allow an unknown finder to calculate how long the probe had been traveling. The assumption, of course, was that something intelligent might find it. But here's what nobody says out loud. The odds of that happening are so close to zero that the Golden Record isn't really a message. It's a ritual. A way of acknowledging that these machines will outlast us, and we needed to send something of ourselves with them. It's the same impulse that makes people carve their names into trees. We know the tree doesn't care, we do it anyway. Voyager 1 reached Jupiter in early 1979, beginning its observation sequence in January. For 4 months, it studied the gas giant, capturing over 19,000 images. The most significant findings came during its closest approach on March 5th. It revealed the nature of Jupiter's Great Red Spot, a storm larger than Earth that has been raging for at least 300 years. It discovered a faint ring system surrounding the planet, invisible from Earth. But the real surprise came from the moons. On Io, Voyager's cameras caught the outline of a volcanic plume rising from the surface. This was the first time active volcanism had been observed anywhere other than Earth. The eruption was spraying material into space at such velocity that it was feeding Jupiter's magnetosphere, creating a glowing torus of plasma around the planet. Meanwhile, Europa appeared smooth, cold, and almost completely craterless. Its icy surface showed patterns that didn't match impact cratering or volcanism. The patterns looked like something else, something underneath. Voyager also mapped Ganymede and Callisto, both ancient and heavily cratered, scarred by billions of years of bombardment. Then it left the Jupiter system, using the planet's gravity to accelerate towards Saturn. It reached Saturn in late August of 1980, making its closest approach in mid-November. The ringed planet revealed itself to be far more complex than anyone had anticipated. The rings weren't smooth. They were filled with intricate structures, braids and gaps and resonances created by the gravitational influence of Saturn's many moons. Voyager measured a day on Saturn as 10 hours and 39 minutes. It observed auroras in the polar regions, complex emissions that hinted at interactions between the planet's magnetic field and its atmosphere. And then came the most critical moment of the entire mission: the flyby of Titan. Titan was the reason Voyager 1's trajectory had been designed the way it was. It's the only moon in the solar system with a thick atmosphere, and scientists desperately wanted to know what was hidden beneath the orange haze. If Voyager 1 succeeded in studying Titan, then Voyager 2 would be cleared to continue onward to Uranus and Neptune. If it failed, Voyager 2 would have to attempt Titan instead, and the ice giant mission would be cancelled. Everything depended on this single flyby. Voyager 1 passed within 6,000 kilometers of Titan's surface. Its instruments detected a dense atmosphere made primarily of nitrogen, with traces of methane and complex organic molecules. The surface pressure was higher than Earth's. The temperature was minus 179 degrees Celsius. The cameras couldn't penetrate the haze, but the data was enough. Titan was confirmed as a high-priority target, and Voyager 2 was officially cleared to continue to the ice giants. Voyager 1's trajectory bent it away from the plane of the solar system, up and out toward interstellar space. It had completed its planetary mission. Everything after this was the extended mission, the part we never officially planned for. Meanwhile, Voyager 2 was still on its grand tour. It reached Saturn in August of 1981, 9 months after its twin. It took a different trajectory, one that kept it in the plane of the solar system so it could continue onward. It studied Saturn's rings, its moons, its magnetosphere. It confirmed findings from Voyager 1 and added new data, and then it left, heading for Uranus, a planet that had never been visited. The journey to Uranus took 4.5 years. Voyager 2 arrived in January of 1986, becoming the first and still the only spacecraft to visit the ice giant. Uranus is strange. It rotates on its side, its axis tilted 98 degrees relative to its orbit. This means its poles experience 42 years of continuous sunlight, followed by 42 years of darkness. Voyager found a planet that was almost featureless, a pale blue-green sphere with barely any visible cloud structure. Its magnetic field was tilted 60 degrees from its rotational axis and didn't pass through the planet's center. Nobody knows why. Voyager discovered 10 new moons and studied the 5 that were already known. It found a system of dark, narrow rings, completely unlike Saturn's bright icy bands. And it detected a strange phenomenon in the magnetosphere. Particles were being trapped and accelerated in ways that didn't match theoretical models. Then it left, continuing toward the final target, Neptune. Neptune is nearly 3 billion miles from the Sun. Voyager 2 reached it in August of 1989, 12 years after launch. It found a dynamic, active world, nothing like the quiet, featureless Uranus. Neptune's atmosphere showed massive storm systems, including the Great Dark Spot, a hurricane-like feature the size of Earth. Wind speeds exceeded 2,000 kilometers per hour, the fastest ever recorded in the solar system. The planet radiated more heat than it received from the Sun, powered by some internal energy source that still isn't fully understood. Voyager studied Neptune's largest moon, Triton, and found something nobody expected: active geysers. On a world with a surface temperature of -235 degrees Celsius, nitrogen geysers were erupting and spraying material kilometers into space. Triton is the only large moon in the solar system that orbits backward, retrograde to its planet's rotation. This means it was probably captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. And if Triton was geologically active, then something was heating it. Tidal forces, maybe. The slow inward spiral toward eventual destruction. Voyager gave us one glimpse, and then it left. That was August of 1989. Both Voyager probes had now completed their planetary missions. Their cameras had seen things no human had ever seen. They had answered questions and created new ones. And now they were heading outward into a region of space we had no data on. This is where the story changes. Because what the Voyagers found next wasn't on any of the official mission objectives. It wasn't something anyone predicted. And it's still happening right now, in the space beyond the planets, where both spacecraft are still functioning, still transmitting data back to Earth. The solar system doesn't end at Neptune. The planets end, but the Sun's influence extends much farther. The Sun produces a constant stream of charged particles called the solar wind, and this wind creates a bubble around the solar system called the heliosphere. Everything inside the bubble is dominated by the Sun's magnetic field and particle environment. Everything outside is interstellar space, the region between stars filled with particles and magnetic fields from other stars, from supernovae, from the galaxy itself. The boundary between these two regions is called the heliopause, and in 2012, Voyager 1 crossed it. It was the first human-made object to enter interstellar space. The transition wasn't sudden, there was no sharp line. Instead, the spacecraft detected a gradual change in the particle environment. The solar wind dropped to nearly zero. The galactic cosmic ray flux increased. The magnetic field orientation shifted. Voyager 1 sent back data showing that interstellar space was denser and more turbulent than models predicted. The boundary itself was dynamic, shifting and rippling as the solar wind pushed against the interstellar medium. 3 years later, in 2015, Voyager 2 crossed the heliopause at a different location, and the data didn't quite match. The boundary was different in different directions. The heliosphere wasn't a perfect sphere. It was asymmetric, distorted by the Sun's motion through the galaxy, by the pressure of the interstellar wind pushing back. Both spacecraft are still sending data. Voyager 1 is currently over 15 billion miles from Earth. Voyager 2 is slightly closer, but on a different trajectory. Signals from Voyager 1 take more than 22 hours to reach Earth, traveling at the speed of light. The spacecraft are powered by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. The plutonium is running out. Power output decreases by about 4 watts per year. Engineers have been shutting down non-essential systems to keep the most important instruments running. The heaters were turned off years ago. The internal temperature is now below freezing. But the instruments still work. Current estimates suggest the Voyagers will run out of power completely sometime in the mid-2027. After that, they'll go silent. They'll keep moving, coasting on momentum, but we won't hear from them again. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. Voyager 2 will pass near a star called Ross 248 inches, roughly the same time frame. They will spend hundreds of millions of years drifting through the galaxy, and the Golden Records will be the only evidence that we ever existed. But there's a fifth spacecraft on an escape trajectory. New Horizons. It launched in 2006, headed for Pluto. At the time, Pluto was still considered the ninth planet. By the time the probe arrived, Pluto had been reclassified as a dwarf planet, but the mission continued. New Horizons was part of NASA's New Frontiers program, designed for medium-cost missions with high scientific return. The goal was to study Pluto and then visit at least one other object in the Kuiper Belt, the region of icy debris beyond Neptune where Pluto orbits. The mission almost didn't happen. It was proposed multiple times and rejected, but in 2002, the National Research Council placed it at the top of their priority list, even above missions to Jupiter and the Moon. The team was assembled mostly from scientists who had worked on previous cancelled Pluto missions. They built the spacecraft in less than 4 years. It launched on January 19, 2006, and spent 9 years crossing the solar system. It passed Jupiter in 2007 for a gravity assist, then entered hibernation. It crossed Saturn's orbit in 2008, Uranus in 2011, Neptune in 2014. On July 14, 2015, New Horizons made its closest approach to Pluto, passing just 12,500 kilometers from the surface. The images it sent back were stunning. Pluto wasn't a dead, cratered ball of ice. It was geologically active. The surface showed mountains made of water, ice, plains of frozen nitrogen, evidence of past and possibly ongoing cryovolcanism. There was a massive heart-shaped region of smooth terrain, later named Tumbor Regio after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. The heart sits on top of an ancient impact basin, filled with frozen volatiles that are still slowly convecting, resurfacing the area over millions of years. New Horizons found evidence for a subsurface ocean. Liquid water kept warm by tidal heating and the decay of radioactive elements in the core. The same kind of ocean that might exist under the ice of Europa and Enceladus. Pluto has 5 moons. The largest is Charon, so big relative to Pluto that the two form a binary system, orbiting a common center of mass that lies in the space between them. Charon showed signs of past geological activity as well. Ancient cryovolcanoes. A frozen ocean. A reddish polar cap made of organic molecules called tholins, created when methane in the atmosphere is broken down by sunlight. As New Horizons left the Pluto system, it turned its cameras back for one final shot. The image showed Pluto backlit by the sun, with a thin haze of atmosphere glowing around the edges. Nitrogen, methane, complex hydrocarbons. An atmosphere that freezes and falls to the surface when Pluto moves farther from the sun, then sublimates and puffs back up as it moves closer. A world that breathes over the course of its 248-year orbit. After Pluto, New Horizons was directed toward another Kuiper Belt object. The target they selected was originally called Ultima Thule, later renamed Arrokoth. It's a contact binary, 2 ancient planetesimals that gently collided and stuck together billions of years ago. It looks like a snowman. New Horizons flew past Arrokoth on January 1st, 2019, at a distance of 43 astronomical units from Earth. The encounter revealed a pristine reddish object covered in tholins, unchanged since the solar system formed. Studying Arrokoth gave scientists a direct look at the building blocks of planets, frozen in time. New Horizons is still operational. It's currently about 58 astronomical units from Earth, all major instruments functioning. It will eventually take another family portrait of the solar system, like the one Voyager 1 took in 1990, but this time, Pluto will be included. After that, it will leave the solar system, following the Voyagers into interstellar space. But New Horizons doesn't carry a golden record. It carries something else. A small container holding 1 ounce of Clyde Tombaugh's ashes. Toombaugh discovered Pluto in 1930 by comparing photographic plates, looking for objects that moved against the background stars. He spent the rest of his life studying the solar system, and he helped with the early planning stages of the New Horizons mission, though he died in 1997, 18 years before the spacecraft reached Pluto. Part of him made it there anyway. His ashes are now farther from Earth than any human remains have ever been, and they'll keep going out into the space between stars. There's something unsettling about the fact that our most distant artifacts are machines we can barely communicate with, moving through a void we'll never reach. They're sending back data about a region of space that doesn't behave the way we thought it would. The boundary of the heliosphere is shifting. The interstellar medium is denser than expected. The magnetic field structure is different in different directions. These aren't minor discrepancies. They're hints that our models of how the Sun interacts with the galaxy are incomplete. And eventually, the Voyagers will stop transmitting. The power will run out, the instruments will freeze, and they'll go dark. After that, they'll drift for millions of years, and the only record that they came from somewhere will be the Golden Records, spinning silently through the void. If something ever finds them, it will be long after our Sun has burned out. Long after the Earth is gone. The record contains images of humans, of cities, of DNA structures. It contains music by Bach and Chuck Berry. It contains a greeting from Kurt Waldheim, the Secretary General of the United Nations in 1977. The greeting assumes that whoever finds it will understand the concept of communication, that they'll have the technology to decode analog, audio and video from a rotating disk, that they'll recognize the pulsar map as a coordinate system, that they'll care. But maybe that's not the point. Maybe the Golden Record was never about communication. Maybe it was about the fact that we sent something of ourselves into the void, knowing it would outlast everything we've ever built. A signature, a mark, proof that we were here. Right now, 5 spacecraft are moving through the space beyond the planets. Pioneers 10 and 11, Voyagers 1 and 2, New Horizons. All of them are leaving the solar system. All of them will drift through the galaxy long after we're gone. And the data they're sending back is telling us that the universe just beyond our doorstep is stranger than we thought. The heliosphere isn't a simple bubble. Interstellar space isn't empty. The boundary between the two is alive, dynamic, shifting in ways we're only beginning to measure. And we're measuring it with machines built in the 1970s, machines that were never designed to last this long, sending back data from a place we've never been about a region of space we barely understand. The Voyagers were supposed to visit the planets and then shut down. Instead, they kept going. They crossed into interstellar space and found that the models were wrong. They're still out there, still transmitting, still telling us things we didn't expect. And when the power finally runs out, they'll keep moving, silent, carrying their golden records into the dark. What they'll find out there, in the space between stars, is something we'll never know. But the fact that they're there at all, billions of miles from anything, still sending data after nearly 50 years, says something about what happens when you design a machine with no expectation that anyone will ever retrieve it. You build it to last. You send it away forever, and then you wait to see what it tells you.